Let's go over the Unit 2 practice problems where we check data integrity, do some data validation checks, work with dates, analyze some missing values, and work with categorical variables and their levels. So if you haven't already done so, you need to install these four packages because we'll be using them in this analysis. And you can just run each line one by one. Now remember, you only ever need to do install.packages once, but we still always need to load up those packages by doing library reg class, library lubridate, etc. All right, so what we're going to be doing is working with the retailer dataset to start out with. And so because this is in a data file, I need to make sure that R is looking in the right place for this file. The getwd command lets you know what the working directory is, basically where R is looking for data files. And right now I'm in the wrong folder. I want to go into the folder that contains information on PracticeSet2. And so I'm going to go into session, set working directory, and I'm going to choose my directory. And in this case, I keep everything organized by assignment, and so I will go into the Practice2 folder. You might have everything in just your one analytics folder, and that's fine. But once we're there, we can run the read.csv command to read in our data because it's in CSV format. And it's a pretty big data set. So we have 135,000 observations, 25 different variables, and let's see what we're going to do with this data. So we're going to load up the lubridate package because that's going to allow us to work with dates very easily. All right, so part A asks us to check out the date column, which is the very first column of the data frame, and to determine the ordering of the temporal information. So right now, if I just look at the first few entries of the date column, I see that it's being stored as a categorical variable. The entries are text, and we have the levels vector, the list of possible values, printed out here. And in order to convert this into a date object, I just need to figure out, okay, well, how are these dates stored? What date information do I have, and what is the ordering of that information? And it looks like in this case, I only have information about the date, nothing about the time specifically during that day. But what I do notice is that the ordering of the information is month, then day, and then year. And when we're working with lubridate, all we have to do is recognize what the ordering of that information is. That'll suggest what the name of the function is in lubridate for us to convert that into an actual date object. So we've determined the ordering of the temporal information, and the command we're going to use is going to be mdy for month, day, year. And we're going to convert the date column into the date time object, actually overwriting the original entries in there. So I'm going to take retailer $date, and I'm going to left arrow into that the current values just after running through the mdy function, since that's the ordering of the temporal information. Watch what happens up here in the global environment. Right now it's a factor with 217 levels. When I run this command, it'll get converted into an actual date object. All right, so now that we've converted into a date object, we're asked to verify that every date in the dataset corresponds to a Monday by using the wday command. So the wday command extracts out the weekday for a date object, and depending on if we add in the additional argument label equals true or not, it'll return either a number or the actual name or abbreviation of the day of the week. So what I'm going to do is make a table of the result of running wday on retailer $date. I'm going to add label equal true so I actually get the name of the day instead of a number. And so we see that everything corresponds indeed to a Monday. Now, the other thing we want to do is to make a bar plot to visualize the frequency of each month and to determine the month that appears most often in the data. All right, so to make a bar plot, the command is bar plot, and what we have to put inside the parentheses is the result of making a frequency table. So we're going to make a frequency table, not of the day of the week because it's all Mondays, but instead we want to get the month out. So the name of the command, not too surprisingly, is month. So we'll run this, we'll get the bar plot out. We might need to resize the window to make all of the labels appear. That's one of the drawbacks about some of the plotting in R is that it's very dependent on the size of the plotting window here. And if we want to just eyeball to see what the most common month is, well, it looks like that's July. The least common month looks to be May here. So we can do some descriptive analytics just by making that bar plot. All right, part B asks us to write a single line of code that outputs the name of the least frequently appearing month, which we can see is May, but how do we get R to tell that automatically? How do we avoid having to eyeball this? All right, so the way that we're going to do this is we're going to start out with a frequency table. That's what we would use to see how often we see each value in a vector of numbers here, or a vector of words. So let's start out by looking at a frequency table of the months. So here, without the label equal true, we just have the month as a number here. So I'm going to add in label equals true so we get the name of the month. All right, so one thing to keep in mind is that the output of table is a very special vector. The entries of that vector are actually the frequencies themselves, these numbers down here. Now, the thing in R is that you can name each element of a vector. Much like each column of a data frame has a name, you can give each name or each entry of a vector a name as well. And you can actually access those names with the names command, much like you would access the names of a data frame. Notice what happens if I ask for the names of this vector here, the names of this table. I get January, February, March, etc. And so what we can do is if we want to extract out the most common, the least common appearing month, is that we can sort these numbers from biggest to smallest and then extract out with that names command whatever we're really interested in looking at. So what I'm going to do is I'm going to sort this table, which is really just sorting these numbers that emerge here. By default, it'll go from smallest up to largest. And, well, that's good, because if I want to extract the least commonly appearing month, well, that's going to be the name of whichever element comes first. So if I ask for the names of this vector, I see that I get May, November, February, etc. up through July. And so if I just slap a square bracket 1 at the very end of this command, that's going to extract out just the first element of that vector, and that's going to be just May. So definitely use this to your advantage here. The output of table is a very special vector. It is a vector of the numerical frequencies of each value in that vector, and each of those elements has a name. So we can sort it and then extract out names with the names function. All right, part 1.2a asks us to do some integrity checks here. So what we're going to start out by doing is printing out the values of the levels vector of the product column. The product column is somewhere down in here, the very last column here. It's a categorical variable with 30 different levels, and so we'll print that out to the screen. Now, very often when you're working with real-world data, categorical variables are going to have issues because the levels might be misspelled. There might be redundant levels depending on capitalization. There might be blank levels, and how you encode a blank is by no means, a well agreed upon activity. Sometimes it might be actual blank. Sometimes it might be a space, multiple spaces. You never know. And so this is asking you to identify some sort of issues with these levels of the product categorical variable. So what we're going to do is try to identify 5 obvious data integrity issues, all of which are going to just arise from the spelling. Now, one of them is given to you, is that fashion D, which is misspelled, should be fashion D here. And so this is just eyeballing it. So we can't have software automatically do everything for us. We still have to give a little bit to that analysis. So scanning down, well, what can we see? Well, one thing that we see is that electronics B should probably be electronics B. I'll write a little note about that. Let's change this, change to electronics B. That's issue number 2. We have that fashion, this is the one that's given to us. We need to change that to fashion D. There's not a separate level already for that. We can just rename that entirely. We notice home A and home A here. We have inconsistent capitalization. So we should change that to home A, home D, home E, jewelry A, jewelry B, C, D, E, other, and other. We have some capitalization issues. We want to change the one in all caps to the one with just the O being capitalized. And then we have this watch and watches A. Now the rest of the watches are pluralized, so we should probably change watch A to watches A. All right, so we've identified the 5 issues, and now we want to fix these levels using the safe procedure. So the way that we change the names of levels, or to combine them, is by accessing the levels vector of that categorical variable itself. So what we're going to do actually is we're going to say, all right, we'll take this vector and take specific elements of that vector and then change that to something else. So how do we know what to change? Well, I could change the 5th level by hard coding bracket 5. That happens to be electronics B, something that I do want to change. But we never want to actually hard code numbers inside the square brackets, because if the ordering of the levels of the categorical variable change for whatever reason, bracket 5 is no longer going to refer to what it used to. If the ordering switches up, bracket 5 is going to refer to something else. So the safe procedure says, all right, well, we need to refer to which element of the levels vector to change, but we'll do this safely with the which command. The which command dives inside of a vector and identifies where inside that vector it finds some sort of element, some logical condition being satisfied. And so the way we're going to set this up is we're going to say, okay, well, the vector we want to dive into is the levels vector. So which entry of the levels vector of the product column here is, and I'm going to, instead of the double equal sign, I'm going to do percentage in. That's a bit more okay, generalization of the equal sign here. Which one of that is equal to electronics B? All right, so if I just run the which command, it'll dive inside the levels vector and it'll identify any elements that are equal to electronics B, which we'll see will evaluate to 5. So a much safer way of referring to where in the levels vector that level is that you want to change. And so if we run this part of the command, we see that we get electronics B, and we're just going to left arrow that to be electronics B. We're going to correct that spelling. So we run this, and then what we have is the results. We don't see this anymore. Electronics B is gone. The levels, we see we have just electronics B. And you'll notice the ordering of the levels now has changed a little bit. Back before, electronics B became after electronics A, but now that's no longer the case. And that's because we renamed this electronics B to be electronics B. So the ordering of the levels of the categorical variable can change when you start manipulating them. That's why you always want to do the safe way. All right, so for the other issues, well, it's all pretty similar in structure, the commands you're going to use. We want to change fashion D to fashion D, correct the misspelling. We want to change lowercase home A to uppercase home A. We want to change capital other to other where just the O is capitalized, and we want to change watch A to watches A. So we'll run these 5 commands, and then we'll just check to see, all right, does it look like we've fixed the integrity issues? We'll print out the levels vector once again. We can scan through and we can say that, yep, it looks like we have done our job. All right, 1.2b asks us to run summary on our fixed product column. So let's go ahead and do that. Extract out the product column with the $sign right after the name of our data frame. And what we find is that some of these categories are really rare. So watches B, C, and D don't really occur all that often. So it might be advantageous to actually combine all these 4 categories, which are referring to watches, into one overall category. So let's combine these 4 levels and actually rename this just to be watches, like right here. All right, so we'll use that safe procedure and percentage in. Now we've already reasoned through how this command works. So I'm going to copy and paste this and modify what we see here. So we're taking the levels vector as is. We're turning on the square brackets because we want to refer to particular elements. We know that we want to take these 4 elements and rename them. So the which command will get us there. the which command will dive inside the values of the levels vector and identify where it finds elements that equal to, well, the elements of the vector that I put to the right-hand side of the percentage in here. So in this case, what I want to do is I want to identify where I find watches A, watches B, watches C, and watches D. I'm basically taking all 4 of those levels. We notice if I run just the which command here, it happens to be elements 23 through 26. I can run the entirety of that left-hand side before the left arrow to just verify that, okay, yes, these are the 4 levels I'm going to be changing, and I want to left arrow them to be just watches. So take these levels, make them equal to watches. We'll run that command, and if we run that summary, once again, we see that we've successfully combined those 4 levels together. And the last thing that we're asked to do is to find the average value of num orders for rows that have this watches in the product category. That's a little less than 320. All right, so how do we get the average? Well, it's the mean function. What are we taking the average of? Well, the num orders column of the retailer data set, but not every row. The average of every row is 145.5. We want to take the average of just the rows that correspond to watches. So what we can do actually is we can turn on the square brackets right after referring to retailer $num orders, and we're going to say, all right, but just pay attention to those rows where we find watches in the product column. So this is a job for which. Which elements do we want to be averaging together? Well, we want to average together the elements where we find inside the product column the value watches. So if I run this which command, this is printing out all of the rows where it finds watches in the product column. And so if I take the average of the number of orders in just those columns, I get that number that's just a little bit less than 320. All right, 1.3 asks us to do an integrity check on these 3 columns, the effective orders TV, online, and effective orders column. Now, logic would dictate that if we took the value in the TV orders and online orders and added them together, we should get the value in effective orders. This is a company that's selling products just on TV and just online, so these 2 orders should add up to be with the number in effective orders. If they don't, well, that's a data integrity issue. There might be some bookkeeping issues. All right, so what we want to do is we want to investigate this. And I've given you a hint here that says, let's just create a vector X that contains the effective orders from online, adds them to the effective orders from TV, and then subtracts off the number in the effective orders column. So let's follow that hint. Let's left arrow into X the values inside the effective orders on TV, add that to the numbers in the effective orders that were online, and then subtract off the numbers that are in the effective orders column. So if there were no integrity issues, we should find that these 2 numbers added up equal to this number, and so X should be 0 for rows that are okay. So I'm going to run this. Now this works because if I just extract out the values inside of a column, that's just a vector of values, vector of numbers, and I can add vectors together. I can subtract vectors as long as they're the same length. So I'm basically doing this element by element. The first element of the TV orders gets added to the first element of the online orders, subtracted the first element of the orders column. So I can do vector arithmetic no problem. So the question becomes, all right, well, do I see values of 0? Do I see values that aren't equal to 0? Let's just get a summary of these numbers. Then we see that there's some zeros in there. The median is 0. The first quantile is 0 here. But we do see some negative values. We see some positive values. So we're asked to find the fraction of entries in X that are not equal to 0. Well, my favorite way of doing that is to take the average of a logical statement. So if I ask, what's the average of the logical statement X not equal to 0? What this will do is it'll evaluate the logical statement X not equal to 0 will return true when I don't see a 0, and it'll return false when I do see a 0. And since R treats false as 0 and true as 1, asking for the average of this logical statement will find the proportion of trues, or in other words, the proportion of entries that in this case are not equal to 0. So what we find is that about 25% of the rows here have integrity issues. So that's not good news. There must be some sort of bookkeeping issues. And in fact, at this company, it makes a little bit sense. The way that they keep track of effective orders is a little bit wonky. So in this case, it's not too big of a surprise for this to rear its head. Now, we're also asked to do this for the net sales TV, net sales online, net sales total. So let's go ahead and just borrow the code that we wrote and just change the name of columns that we're extracting. So we want net sales online, net sales TV, and net sales tote. So presumably online plus TV should equal to total. We take a summary of this. Looks like the smallest value is 9. In fact, every single value is not equal to 0 here. So this has substantial integrity issues. The bookkeeping at this company is kind of weird. So we have a lot of issues. About 25% of rows have issues with regards to orders, and all rows have issues with regards to sales. The bookkeeping is wonky at this company, and so these things aren't adding up as we would have logically anticipated them to. Now, it makes sense for this company. Their internal logic is saying this is an okay thing to do, but from a data point of view, it's kind of a weird thing. All right, 1.4 asks us to go through the process of maintaining data integrity, going through each column methodically, one by one, checking to see if any of the values are wrong, making sure all the values do make sense, and going ahead and fixing any sort of issues when they crop up. So in this case, we have 25 columns, so we're going to have to do 25 different operations here. And this is just the sad case of being a practitioner in data analytics. Very often, 80% or so of your time is going to be spent cleaning the data, making sure it's in a place where we can actually do analytics. We can't do any algorithms and learn anything about the data if the data is not good. So the tools that we have for maintaining and examining data integrity are looking at a summary of the values, making sure the biggest, smallest values look fine, ensuring that the class of the object, character, factor, integer, numeric is right, a frequency table just to make sure there aren't any weird values. We get a table of each unique value and how many there are. Looking at head, tail, etc., just to check to see if everything is fine. So in this case, we're supposed to go through each one of those columns one by one, examine to see if there's any integrity issues, and if there are, fix them. All right, so let's go through each of them one by one. So starting with the date column, we've already fixed the issue where it was read in as a factor, and we've made it into a column that contains a date format. So it just suggests to run the summary function on this column just to get an idea for what we have here. So we have no issues. We can see that the soonest date, or the one farthest back in the past, is June 27, 2011. The most recent one is from August in 2015. All right, price category is a price bin. It should be a categorical variable with a certain amount of levels. Well, let's take a look at the class, the type of object of the price category column, and we see that's an integer. Well, that's no good. We want it to be a categorical variable. If we look at a table of all the unique values, we see that, okay, yeah, there's not too many unique values, so it's a good idea to convert this into a factor. So how do we do this? Well, we're going to left arrow back into the price category column, just the original values after running it through the factor function. So once we do that and we make a table, we see the same frequency table as we had before, but we see the price category now is a categorical variable. So we make this into a factor. Numprod is the number of products shown on TV in the product group over all broadcasts during the week. Should be integer, 0 or greater. So we can ask for the class of this column. And it is integer, great. So if we look at a summary of the values, we see the smallest is 1, so there's no issues here. No zeros, no negatives. This is good to go. Showings should be integer, 0 or greater. So let's borrow the code that we just wrote. Let's go and look at the showings column in terms of its class. Integer, good. A summary, smallest value is 1. No issues. 0 or something smaller would have been bad, but we don't see that. All right, duration, total number of seconds the product group was featured on TV. Needs to be numerical. 0 is okay because it might be the case that, all right, it just wasn't shown that particular week. It was in other weeks, but maybe not that week. So the class of the duration column is integer. It's the number of seconds, probably just rounded to the nearest second, so that sounds good. And a summary of this column, we go anywhere from 0, not shown that week, to this large number. Is this a reasonable number? Well, let's convert seconds into minutes. That's 561.1 minutes, and let's convert that into hours. So that's 9.35 hours. That feels pretty reasonable for an entire week showing. So looks like there's no issues. Maybe check to see, sorry, that's my dog snorting. Maybe check to see if 9.35 hours is a reasonable quantity with people who are in charge. So maybe some follow-up, but no immediate red flags there. All right, so viewers, well, I don't have a bullet point for that. Let's put that there. Viewers is something mysterious. Let's take a look at the class of it. It's integer, and we go from 401 to 102,000. So I'm pretty sure the viewers is the total number of viewers over all showings for that week. Let's go with that. So can be 0 if not shown, and it must be integer. All right, so we do see that it's integer. It goes from 401 to 102,000. So it looks okay. 102,000 seems like a lot, but I think it's likely okay because there might be some product group that was just featured a lot on television for that particular week. But we could always follow that up and check just to make sure. All right, net revenue over all showings of that product group has to be numerical, so we can check the class of the net revenue. And it's integer, so that's great. And we can look at the summary of it. And we see it goes from negative 745 up to a pretty big amount, almost kind of getting close to $1 million there. So our negative value is okay. Well, yeah, they are in this case. If we had some returns, discounts, if it was actually being sold at a loss. So I would say that there's no issues. 703,000 is a really big number. So we might want to follow up on that. But no logical red flags from there. All right, gross margin. Well, it should be numerical. Negative values are okay since the product can be sold at a loss. So we can look at a class and the summary of this. It's integer once again, and we do see negative values and positive values here. So no issues. That's losing a lot of money for a week, but hey, that might just happen. Product discount is the average discount in percentage form between 0 and 1 written as a decimal for all products shown in that group. So it needs to be numerical. All values should be between 0 and 1. And let's quickly check on the class of it. It's numeric, that's good. A summary, the smallest value is 0, the largest value is 79%. So no issues. Everything's in the range it should be. Shipping discount, very similar, just the discount applied to shipping. So let's quickly examine the class of this column. It's numbers, as expected, and a summary of the shipping discount. They all range between 0 and 1. The expected range, so no issues. Number of orders. So the number of orders of all products shown in that product group should be integer greater than 0 or 0. Maybe nothing was actually ordered for that product group. So let's take a look at a class. Integer, perfect. A summary of it going from 0 up to 14,500. It's a pretty big number, but who knows what that actually corresponded to. The data is anonymized. We could always follow that up or follow up on that if we wanted. So we could follow up on that just in case, if we had a little bit more domain knowledge, we'd know if that was a reasonable big number, if that seemed to be a bit out of place. All right, total sold, total number of items sold. This is going to have issues. I'll give you a little hint on this. And there's two things that we're going to look regarding this column, two lines of investigation. So first of all, let's look at total sold. The class of it is numeric. All right, that seems okay. Should be integer, of course, because you can't sell a fractional amount of items sold, but sometimes integers just are numeric columns. We won't worry too much about that. But it asked us to, all right, really make sure that it's integer. So let's just get a glimpse at maybe the first 10 values. Turn on the square brackets, 1 colon 10. Let's print out the first 10 values. And what's up with this? 7.94, 258.26, 7.98. This is weird. Why are we seeing these decimal amounts in this column? All right, so let's determine the fraction that aren't integers. Let's go ahead and look at a summary of this column. So it goes from 0 up to this pretty big number here. How can we check to see which are integers or what fraction are not integers? Well, one thing that we know is that there's a logical condition, percentage in. And what percentage in is going to do is it's going to allow us to dive into the vector on the left-hand side of the in and check to see if it finds elements in a vector that we give to it on the right-hand side of percentage in. So one way that we can determine whether or not a value is an integer or if it's not is on the right-hand side of the percentage in, give it the integer sequence 0 up to some big number. Let's go 14860. We don't know if this is 0.00000, if it's actually an integer at the maximum, or if it's a 0.01, etc. So why don't we go up one larger than that largest value here? So here's the integer sequence, 0, 1, 2, 3, 4, all the way up to the maximum value here. So if we check to see if the values inside this vector match up any of the numbers inside this integer sequence, then that's going to be basically coming out with a true or false for if we do find an integer or not. So we see a lot of trues, a lot of falses. If we ask for the average of this logical vector, well, true is 1, false is 0. So this is telling us that about 80% are integers. 1 minus that would tell us the fraction that are not integers. So about 20% are not integers. Or if you don't like doing the 1 minus trick, we could ask the opposite of this question. So total sold, percentage in, this integer sequence is true if it's an integer, false if it's not. If I put an exclamation point in front of there and then wrap this in parentheses, this is asking, all right, is it not an integer? Kind of negates that logical expression. So same sort of issue here. We get 20.3% being non-integer. So about 20% of values are not integers, so that's bad news. And then also, if we think about it, the number in the total column here should be equal to or greater than the number of orders. Now, sometimes the number sold is going to be bigger than this number because you might order more than one of that particular item. So we can check to see, well, what fraction of rows have an issue with regard to this criteria, this logical criteria. Why don't we take the average of the logical condition, retailer total sold, being greater than or equal to retailer $ total orders. Which is that total orders column? That's when we got to dive back in, forget all the column names. We have effective orders. We have total sold. That's when we're looking at num orders is what we want. Okay, so this logical condition right here is going to return true or false for if this value is at least as large as this value. So if we take the average, that'll tell us the proportion of elements that are equal to true here. In other words, the fraction that seem to be legitimate. So the ones that are not legitimate, well, those would be when total sold is less than the number of orders. And so we find that about 8.5% have it where the total sold is less than the number of orders. Integrity issue because logically that can't happen, but we know that this company, some weird bookkeeping stuff is going on, so that would probably explain it. All right, cost of goods. The total cost of goods over all products in that category. So one thing that we know is that things cost something, so we shouldn't have any zeros, but we don't have to have them be integers. So let's look at the class of cost of goods. It's numeric, so that's good. What about a summary of cost of goods? Well, we see some zeros. Looks like there's some really expensive product categories for the week. That definitely should maybe look, or should require looking into. The largest value of 461,037 should probably be investigated. That's really quite large for this company here. With extra domain knowledge, we'd be able to make a better judgment call. But we do see some zeros. So we do see zeros, and this doesn't make sense. So in this case, since 0 doesn't make sense, we should probably replace it with a missing value because it did cost something, we just don't know what it is. So how can we replace these zeros by NAs? Well, we know something about the which command. We can take the values in the cost of goods column, specifically where we find zeros. So we can ask, all right, square bracket turns on positional reference inside that vector. And we want to know the positions where we have values equal to 0. So which retailer $ cost of goods double equals 0, true or false depending on if there's a 0 there or not. And this is printing out the positions where we find 0. So in fact, if I highlight this whole thing, these are all going to be zeros here. Yeah, the values in these particular positions of this vector are all equal to 0, and let's NA them. Now remember, NA, no quotes ever. NA is our special representation of a missing value. So we'll do that. We'll check the summary once again. And now we have the smallest being 40 cents and a lot of NAs. So we fixed that. All right, price. Average price of all products sold in that product group. Can't be 0 because things cost something here. Not exactly sure what the largest value should be, but let's do some investigation. Should be numeric. It is. A summary of it, we don't see any zeros, so that's good. This largest value should definitely be investigated, though. That's a pretty large price for this company. With extra domain knowledge, we could probably make a better judgment call. But the largest value of this should be investigated further, just to double check that's legitimate. All right, markup should be some number. How much the markup was for the particular product. It is a number, that's good. We look at a summary. Well, it's negative, which is odd, with a maximum of 1. So we're told in this case that the way this is being recorded that it needs to be between 0 and 1. So we do see some integrity issues. So we do see issues in that there are negative values. So why do we see those here? We could take all the values that are negative and just replace them with NAs. Very similar to what we did up here. Basically say, all right, let's dive into that markup column and let's find the positions where we find values of markup that are less than 0 here and NA them. But it's probably more important to actually go and investigate why we would see negative numbers here. Why was that recorded? What's the story behind that? For now, we can just take them out, and if we get a summary, we get from 0 up to 1, 237 different rows that have that issue. All right, net revenue TV is the net revenue from callers during a TV broadcast. Negative, positive is fine. It just needs to be a number here. Sometimes things are being sold at a loss. And so we can just check to see, do we have numbers? Yep. What's a summary? Negative, positive, some really, really good performances here. It looks okay. Net revenue online, well, same story. Positive, negative can be okay. We just need to make sure that they're numbers. Let's go ahead and look at the class of it. They are. And it looks like online's doing a little bit better than on TV. Maybe TV is an outlet where they sell, things they just got to get rid of, and those aren't being featured online at all. So we actually see the smallest value being positive, largest value being really big. No issues. All right, effective orders. Well, we've analyzed this a bit already. We know that there's some wonky bookkeeping practices at this company, so all we're going to do is just check to make sure that they're integer here. Effective orders can be negative if things eventually get returned due to bookkeeping returns and when that product is ordered isn't actually matched up correctly. So we're just going to make sure that we have integer amounts. So it is integer, great, just to get an idea of what this looks like. Here are some negative values, sometimes lots of stuff being sold. So there we go. So effective orders on TV. This is subject to the same issues here, where there are some returns. We just need to make sure that it's integer, and it is integer. So no issues, no other issues, no other issues. And same sort of thing for online. We're going to see the same thing here. We just need to make sure that we have integers. Negative values arise due to weird bookkeeping practices. We do see that there's all integer values. Net sales total can be positive or negative here due to weird bookkeeping practices once again. So we'll just keep track of whether or not we do have integers or not. It is integer. We do have some negative values, big positive values. There's no further issues here. Net sales TV, yeah. So you can start seeing this. This just gets, rather tedious. We're just doing this again and again and again, but it's something we have to do. We can't do analytics until we know that everything is okay. It's integer. Negative values in this case were okay because of weird bookkeeping issues. Same sort of thing for net sales online. Are we integer? We are. We got negatives and positives, so no further issues. All right, so this is what we do. We just go through methodically, column by column, make sure everything that should be a number is a number, make sure everything that's a categorical variable is a categorical variable, make sure that the levels of categorical variables are spelled right. We can combine rare ones together. We can, do whatever we really want to make our analysis easier. We just need to make sure that each number is valid. Sometimes there are logical constraints that relate columns together, like 2 columns should add up to a third, 1 column should always be bigger than another. Sometimes numerical values need to be in a certain range, maybe just all positive, no zeros. Just things we got to put on our thinking cap and make sure that everything's correct. But it's something you have to do every time you're handed a set of real-world data. It's very rarely going to be the case that everything is exactly what you expect. All right, question 1.5 asked us to make a histogram of the net sales total. So in this case, we make a histogram, and like a lot of things in business analytics, the histogram of the originally recorded values, not all that useful. So all the information is compressed inside this one bar here, and that's because we have a highly skewed distribution. So some rows have very large values of net sales total, and the way the histogram is being constructed, the bars just all have equal width. And so there are some values out here that we can't quite see because there's only 1, 2, or 3, etc. But we might have a huge number of values in just a few bars. So unsurprisingly, like everything in business analytics, it seems it's strongly skewed towards the right. And our trick is to often employ logarithmic transforms. Instead of analyzing the original values, let's take the log base 10 and analyze those. But in this case, we can't just straight up take the logarithmic transformation, because if we look at a summary, we see negative values. We can't take the log of 0, and we can't take the log of negative numbers. That's a forbidden operation. So if we wanted to do this logarithmic transformation, well, there's a trick we can do. We can add a constant to every single value in our column here. So what number do we typically add? Well, my favorite trick is to make it so that the smallest value becomes 1. So if we add 1282 to every single value, that's going to make the smallest value equal to 1, and we can take the log of the result here. So in this case, if we take a histogram of the log base 10 of 1282 plus the numbers that we see in that column, now we're looking at a distribution of the logarithms, but we've added 1282 to everything in order to make this log transformation trick work. All right, so much more palatable presentation of the histogram here. We get a little bit more detail of what values we see. Now, because we added something to every value before taking the transformations, we can't say that 4 is equal to 10 raised to the 4th power or 10,000. We'd have to do a little bit of math to figure that out. And so how do we actually do that math? All right, so what's the average value of the transformed quantity? Well, let's just take a look at the average value of the log base 10 of 1282 plus this guy right here. That's 3.738, let's say, after rounding. What does that correspond to on the original scale? Well, if I didn't have to add anything to unlog something, I just take 10 and raise it to this quantity. So I would get out 5470. But because I did add everything, or did add something to every quantity, I need to take 10, raise it to that value, and then subtract off that quantity. I have to give it back. So 1282 subtracted from that transforms this back onto the original scale, so about 4188. All right, part 2 asks us to look at the Bulldozer Blue book here. So once again, confirming that I'm in the analytics folder that I want to be in, where the data file lives, let's go ahead and read in the Dozer data. So according to the data dictionary, this sales ID should be a unique identifier of a sale. Or in other words, we shouldn't have any duplicates. Every value should be unique here. And we're asked, is this the case? There's a good data integrity check here. So 2 ways of doing this. Unique is going to print out a vector of the non-duplicated quantities in this column here. So if there are 1,000 unique values, that means that all values are different because we have 1,000 observations. So if we say length unique, we see 1,000, so that indicates that yes, I don't get any duplicates in this sales ID column. So this counts up the number of unique values, and we see that that's equal to the number of rows. Great. Now there's another way, and that's using the duplicated function. Now I like the duplicated function because it returns back trues or falses. It returns back a false if we've never seen that element before, and a true if we've seen that element before somewhere previously in that vector. So one thing we know about R is that false is 0, true is equal to 1. So if I take the sum of the result of running duplicated, that's going to give me the total number of duplicated elements in the sales ID column. And I get 0 here. So no duplicates. No duplicates. They are all unique. Great. 2.2. The column year made gives the year in which the bulldozer was manufactured. So all entries are integers, but do they all make logical sense? So let's run a summary just to see. Well, no, they don't. What are these 1,000s here? That doesn't make any sense. Let's look at a frequency table of all the different years we see in the data. 1955, well, potentially. That doesn't seem to be illogical. But these 1,000s definitely are bogus. So 1,000 is a bogus entry here. So probably 1,000 equals unknown, or just not recorded in this case here. All right, so to confirm that they all are integers, we can use that class function once again as suggested in the problem. They all are integers, but we see some thousands. That's totally bogus. Let's fix that by replacing unacceptable values with NAs. So how do we do this? Well, what we want to do is we want to take the values in the year made column, not all of them though. Let's turn on the square brackets and refer to the positions that we want to change. Which positions do we want to change? Well, we want to change the positions that have 1,000s. So which dozer $year made double equals 1,000 is going to tell me which positions inside the year made vector here, the column, where I find those 1,000s. If I print out the entirety of this guy right here, I'll just see all 1,000s. I want to change all of those to be NAs. So let's left arrow that to be NA. No quotes because NA is a special symbol in R. And let's see if we fix this. Yep, 1955 is the smallest. 2009 is the biggest, 85 NAs. All right, the column machine current hours gives the current usage of the machine in hours at the time of sales date. 0 means new, and we shouldn't have any of those because none are brand new at this auction. And there's actually 2 data integrity issues, so let's just take a look. Let's get a summary of machine hours current meter. Oh, we see a lot of zeros here. So zeros, that means brand new, which is logically sound, but one thing we know about this auction is that brand new bulldozers weren't being sold ever. So 0 probably just means it wasn't recorded. We should replace those with NAs. So let's do that. Let's use the same syntax as what we did up here. Instead of replacing thousands with zeros, let's go ahead and replace the ones where we see zeros with NAs. Let's just confirm that, okay, we're referencing the correct elements of the machine hours current meter. Yeah, these are all the zeros. So let's get rid of those. And let's look at a summary once again. All right, 33 being the least used, 33 hours, almost brand new. That's fine. Now, I say that there's 2 data integrity issues here. So what's the other? These are all normal looking values. They're all positive at this point. It all shows being used. And so here's where we have to put on our thinking cap. This value right here, all right, that's pretty big. Let's think about what this corresponds to in terms of usage. So this is in hours. All right, there's 24 hours in a day, so let's divide this by 24. That means it's been used for a total of 15,583 days. Well, that's an awful lot. Let's convert that into years by dividing by 365. That implies that this bulldozer has been used for basically 42.7 years. Now that seems awfully fishy. Let's do some further investigation. So 42.7 years, yeah, right. So which row has this obscenely large value? Which of these rows is equal to this 37,400? Now, here's a mistake you'll probably make. I still make it all the time. A single equals sets equality, double equals checks equality, and I need to check to see which one is equal to 374,000. All right, so dozer in the 807th row here, let's just take a look. Here's the sales ID, the sales price. Now, one thing that we can do to just see if this 42.7 years makes any logical sense is to check the year made. Well, this was made in 2005. It's literally impossible for it to have 42.7 years of usage on it. So this is a bogus entry. All right, so the 374,000 hours is bogus since that's 42.7 years of usage, but it was made in 2005. So that's an issue. We should probably get rid of that. And while we're at it, let's just take a glimpse at some of the larger values in this column here. Let's sort this, and let's add in decreasing equals true. And let's look at the first, say, 10 values. So we go from 374,000 down to 30,767. What is that in terms of days? In terms of years? 3.74 years. Well, that seems a little bit more reasonable. We could do the same investigation here. So now you're getting the idea of, okay, there is some sort of logical constraint between what we see in the machine hours current meter and the year made column that we should probably check. We're going to forego that here. We'll just point that out in this case. Let's see which one. Oh, my dog's snoring again, so that's making me laugh. 32767. Well, that's actually in 2 of these rows here. So let's see. Does this make logical sense based on when the bulldozer was made? In this case, we have them being made in 1990 and 2003. This 3.74 years is reasonable. So not an impossible from a logical point of view sort of thing. So we should only necessarily get rid of this totally bogus one, the 42.7 years. So we could say, all right, let's go back into this machine hours current meter column. Let's take out that value that was so big, whichever value is equal to 374000. Let's NA that out. And so now when we get a summary of this column, the largest value is this guy. Seemed reasonable, but we should probably check to make sure that the machine hours current meter is consistent with the year made. But it looks like we've fixed basically the integrity issues that we're obviously aware of right now. All right, moving on to 2.4, we're going to investigate the levels of the FI secondary description column. So levels is the command that we want. Let's get out the levels of this. So without domain knowledge, it's a little difficult to tell whether or not these levels do or don't have issues. We don't know which of these describe valid levels, which of these might represent just missing or unknown. This blank is a good indication that that just means missing or unknown there. But we're not exactly sure about the spelling, all of this stuff. Is X and XT really the same thing? We're not exactly sure here. However, there is one that we can identify, and that is, looks like C appears twice. It looks like we have C just all by itself, and then C with a whole bunch of spaces. Now, maybe this actually does mean two different types of secondary description, or it might just mean that the person recording this inputted in some extra spaces by accident. And in fact, we can get a little bit additional insight by looking at a frequency table of all these levels. This C with all those spaces appears exactly once, so that's probably a typo here. All right, so what is this issue? We see a C with a lot of spaces as a level, and it only appears once. And what we want to do is we want to fix it now. So in this case, we're not going to replace the blank level with NA. We'll keep that as blank just to represent missingness. We could probably rename blank to be missing if we wanted. But let's go ahead and fix this issue with the C at least. So the way that we are going to rename the level is the safe way. So we'll take that levels vector, and then we'll use the square brackets to refer to the position of the levels vector that we want to change. Now we know it's the 1, 2, 3, 4, 5, 6, 7th level, but we're going to specify that through the use of the which command. So we'll ask, okay, well, which position of the levels vector is equal to, and I'm going to copy these double quotes and what's in the middle. I don't want to count up the number of spaces. The copy paste is a little bit easier. So if I say, all right, well, which element of that levels vector do I see this particular value? I see that it's the 7th. So I'm going to take this level and I'm going to rename that to just be C in quotes. So I've fixed it. You'll notice now I'm back up to 111, 110, and that 1 got combined. How would I rename that blank to be missing? Well, very similar. Basically what I would do is I would take the blank level, the pair of double quotes with nothing in the middle here, verify that that's the way that it is spelled. Yep, that comes out. And I could say maybe that's unknown or missing. Up to me what I want to call that, but that's how I would fix that blank level if I wanted to actually replace that with a real word. So there we go. All right, so we made this frequency table, and we saw that some levels are actually really quite rare. So EX appears exactly once, PT once, TM once. It might be the case that we would like to combine some of these rare levels into just a new level called rare, or combined, or come up with some name just to represent that this is like a one-off. We don't really see these all that often. Now, in Reg class, once you've loaded it up, there's a command called combine rare levels. We can bring up the help menu by doing !, combine rare levels. And it says, all right, give me a vector of categorical values here, and then give me a threshold, a numerical value like 20. And what it's going to do is it's going to combine all those levels that appear threshold or fewer times into a new level called combined. And in fact, it's going to output two different things. So in order to get the newly recoded levels, we'll take what the output is from combined rare levels, add a $ values to get that out. So what we're going to do is we're going to replace the values in the FI secondary description column with the output of running combined rare levels with a threshold of 50. So what we're going to do is we're going to take, since I don't feel like typing, we're going to take the values as what we have right now, and we're going to replace them with the result of running combining rare levels with a threshold of 50. The command's given to you $values so that we actually get out the new values. If I don't have that, just so you know, if I were to just run this by itself, it outputs two things, the list of new values, and then also what got combined into that new level called combined. So that's why we have the $values. So we run it, we replace those values, and then we can get a frequency table of the result, and there we go. Everything appears at least 50 times. All right, 2.5 says that many categorical variables in this dataset have a common integrity issue. So let's look at a summary of this particular column as suggested, the turbocharged column. Let's figure out what it is. All right, so we see a blank 823 times, none or unspecified 172 times, and yes 5 times. So what's the difference between blank and none or unspecified? Well, there's probably no real difference here. These two things should probably be combined into the same level, none or unspecified here. So blank and none or unspecified should be combined. In fact, a lot of columns have this exact same thing. We have blanks, but then we also have none or unspecified. So how do we combine these columns, or these levels? Once again, we'll do the safe way. Here's the vector of our levels. We want to replace this first level with none or unspecified, but we'll do this the safe way. We'll say, okay, which element of the levels vector do we want to change? Well, we want to change the one where we find, which levels, $turbocharged, find just that blank. So that's the first level, or first entry of the levels vector. And so we want to change this to be just none or unspecified. So I'll copy this with the double quote, so I just make sure I get the spelling right. And there we go. Now we can get a table of our fixed column, and we just got two levels, yes and no. All right, now let's deal with the stick length column. So the stick length column is a mess. If we look at the levels of this, what do we end up seeing? Yuck. So we see a blank, and we see lengths that look like feet and inches, but some weird additional symbols here. So the single quotation mark is, standard shorthand for feet. The pair of double quotes here represents inches. But the weird thing is we see a backslash, double quote, and then another double quote. So what's going on here? Well, the left double quote, sorry, my dog's snoring again. The left double quote and the right double quote represent the fact that we're treating this entry as text. So this double quote right here is what's actually representing inches. And the backslash right in front of it is our special way of saying, hey, treat this as the character double quote instead of our shortcut for referring to something as a text object. All right, so now what we want to do is a few things. Well, number one, this blank and this none or unspecified, that's really the same thing. So we want to combine these two together. And in reality, if we're going to do analytics, maybe we actually want to convert the levels of this categorical variable into actual numbers. Instead of 10 feet, 10 inches, let's have actual just the total number of inches. All right, so in this case, instead of actually combining blank and none or unspecified into a new level, because we're looking forward and we're going to be replacing these with numbers, we're going to just NA those two levels. So here's one thing that we can do. This is kind of clever here. So here's our vector of levels. Well, which positions in that levels vector do I see this none or blank? So because I'm looking at two of them, I'll do percentage in, blank, and none or unspecified. So where do I find either one of those two levels? It's the first and 16th, for not the entirety of that. Watch what happens when I left arrow this to NA. So when I do this, and now print out the levels vector of stick length, actually that those levels literally no longer exist. I've replaced those with missing values. Okay, so we've deleted those levels here. And we can just check to see, okay, do we have the correct number of levels? It's suggested to be 14. It's 14, great. So now, replacing these with numbers, the number of inches. So I suggest a method of doing this. You could go through and just hand calculate all these things, but here's what I'm going to do. Is I'm going to go through and create a vector called inches, where I go through and figure out, okay, 10 feet times 12, that's 120 inches plus 10. So we're going to create a vector whose entries are the number of inches for each one of these levels. And I've got you started here. 10 times 12 plus 10, then 10 times 12 plus 2, 10 times 12 plus 6, 11 times 12 plus 0, 12 times 12 plus 10, 12 times 12 plus 8, 12 times 8 plus 10, 12 times 8 plus 2, 12 times 8 plus 4, 12 times 8 plus 6, 12 times 9 plus 10, 9 times 12 plus 6, 9 times 12 plus 7, 9 times 12 plus 8. All right. So here's a vector containing these stick length levels, but in inches. Now, because that was so easy to typo, and you saw me do typos like 3 times, I'm going to do a summary just to make sure that, okay, these numbers are matching up. Looks pretty good. All right, so what we're going to do is we're going to rename en masse every single level of the stick length vector. All right, so those are stick length right now. If I look at the levels, here's my levels. What I want them to be are just the entries that I find in inches. So do I have the correct number of levels here in my inches vector? 14, that looks good. So I can rename these en masse by just giving it a vector of new names. 14 levels I want to rename, a vector of length 14. It'll go through and rename those appropriately. Now, inches was a numeric vector. Is that going to mess with anything? Well, no. Because what's going to happen is that R is smart enough to realize that, okay, we're still working with a categorical variable. These levels are still being treated as text, so those numbers got automatically converted into text. Do we get the expected output for the frequency table? Yes, we do. Great. Now we need to convert the values in stick length from levels of a factor to numbers. And then here's the weird thing about this. So let's look at the first 10 entries of the stick length. Well, those are all NAs, so that's not very informative. Let's do the tail. Okay, well that's not very informative either. Which are not NAs here? Let's get an idea. All right, we don't have many non-NAs, so let's actually look at specifically the elements in just a few of these positions. So the 33rd, 158th, 244, those 3 are good. All right. So here's the stick length in inches, but these are levels of a categorical variable. You might think that if we run as.numeric, we would just take these values and replace them with their numeric equivalents. No, 5, 3, and 8. Where do these 5, 3, and 8s come from? Well, when we run as.numeric on a factor, it gives us numbers back, but those numbers correspond to the alphabetical position in the list of levels. So 154, that's the 1, 2, 3, 4, 5th element in the levels vector. 126 is the 3rd element. That's where this 5 and this 3 comes from. So what do we do? Well, what we need to do is we actually need to first convert the categorical variable into text. If we do as character of these 3 elements, we get the character vector 154, 126, 98. Notice we don't have the levels associated with that. Now R will convert character to numbers just fine. And so the final step is to take the values we see in the stick length column and run it through as numeric as character. And so once we do that, Now what we have is a column of stick length in inches. We've converted from levels of a categorical variable to actual numbers that we can analyze now. And there we go. The average is 121.3. All right, 2.7 asks us to examine the backhoe mounting column of the dozer data frame. And we're asked, do we think this column, should it be a part of this data set? Why or why not? If it is needed, fix the integrity issue. If it's not, null it out. Well, here we go. 2 levels. One's a blank, one's none or unspecified. This really means the same thing. We just don't know what it is. So we don't need this column. It doesn't contain any information. It's, for all intents and purposes, just the same value. So we can null it out here. So take those values, null it out. Boom, that column is gone. It doesn't even know about it anymore. So blank and none or unspecified refer to the same thing here. So for all intents and purposes, all values are identical. If all values are identical, it doesn't contain any real information about this these bulldozers, so we can get rid of it. We only learn when there's some variation in values. We don't learn much from just seeing the same thing again and again and again. All right, sale date column. Let's get some practice looking at dates. Have that lubridate package loaded up. Let's use the head command on the sale date column and spy the ordering of the temporal information. That'll tell us the function from lubridate that we need to use to convert this from a factor, which it is currently stored as, into a bona fide date object. So right now, sale date's categorical variable with 763 levels. We want it to be a date object because we want to start extracting out temporal information. So what do we see? We see the month come first, then the day, then the year, and then a space. Then we have information about the hour, and then the minute. Nothing about seconds or anything. So we know that the command we need to use is day, month, year, underscore, hour, minute. The ordering of that temporal information with an underscore separating the day and month information from the time of day information. So if I run this command on the sale date column, I'll get out bona fide date objects right here. And so what we can do is we can overwrite these values in the sale date column with those actual values. All right, so we're getting the 630 entries failed to parse here. Let's do some investigation actually before this, because that's a little bit of a surprise to me right now. So dozer sale date 1. I want to make sure I got this right. I might not have gotten it right here. So that is month. See, it's a typo. It's not day, month, year. It's month, day, year. 6 is June. That's the month. 17 is day. So D. So there we go. Always good to double check your work. So running this, we get a vector of all these dates. So now we can replace that in there with no sort of issue. If I ran that command and I left arrowed that into sales date, I would have wiped out the original values in sales date. There's no undo, so I would have had to gone back, read in the dozer data frame, and then just ran all those commands I ran previously to get back to where I started. So, overwriting the values in the column, really dangerous work. Kind of want to make sure that it's going to take correctly before you run it. All right, so we've done that. We've converted it. And now we're going to create vectors auction month and auction day that give us the month and day of the week that these auctions occurred on. So month, to get that out, it's the month command. Now, if we just run month on the sale date column, we get numbers out. 1 is January, 2 is February, etc. Let's add in the label equals true argument so that we actually get the names of the month out, or at least the abbreviations for them. So we got that. And then the day of the week, the command is wday. Just like with month, label equals true will give us the abbreviations. Without the label equals true, we just get 1, 2, 3, 4, 5, 6, 7. So there we go. There's auction day here. All right, using table, we're making a bar plot to determine which 2 months that auctions are most frequently held. So let's look at a frequency table of auction month. All right, well, we could go through those numbers and look for the 2 biggest ones. Visualizations very often are going to help in this case, so we could make a bar plot of this table. All right, two most common months looks like March and February in this case. So it's not labeled because I didn't give it enough plotting area, but I can kind of eyeball it to see that's the case. Now, how would I have done that without actually doing a visualization? Well, remember the cool thing about the table command. If I do table, that outputs a vector of numbers. Now, the special thing about those numbers is that each of those numbers has a name, much like each column of a data frame has a name. And I can extract those names with the names function. So January, February, March, corresponding to the order of the numbers that appear. Now, because this is a numeric vector, I can sort these values. So I can say sort the results of this table. Now it goes from smallest to largest up by default, but if I add in decreasing equals true, that's going to start at the largest and go down. So, all right, here's my vector of frequencies. Each of those numbers have a name, March, February, etc. I can extract those names out to get the most common, second most common, third most common, etc. And if I just slap on some square brackets, 1, 2, we'll print out the most common and second most common. So kind of cool there. I like doing that. So that's the most common month. What about the day? Well, let's do this. I've already written this here. Let's get the most common and second most common day of the week. Thursday and Tuesday. Let's make that bar plot just to see the visualization as well. Let's confirm that that code worked. Yeah, Thursday the most common, followed by Tuesday, Wednesday right behind there. All right, 2.9 asks us to look at the sales price column and to make a histogram of it. And guess what? We're doing business analytics, so we're going to find a really skewed distribution. It seems to be always the case here. And that's indeed what we see. This actually isn't all too bad. This histogram is pretty informative. It lets us know that most of the prices are around $20,000, but we do see some fairly rare, fairly large prices here. So this distribution is skewed like almost everything in business analytics. All right, so in this case, one thing that we know is that most algorithms in business analytics work better when the distributions are roughly symmetric. So when we see something that's skewed like this, we might want to try to transform the values so that the distribution looks more symmetric. So let's do our go-to transformation. Let's look at the log base 10s of these values instead. Now, can I do log base 10? Well, let's do a sanity check here. I know I can't do a log of 0 or negative numbers, but the smallest value is 5,000. So yeah, I can do logs. Let's look at a histogram of the logs. And now isn't this nice? This looks pretty symmetric here. This is where most algorithms in business analytics and statistics are designed to succeed. So, all right, we're going to create a column called log sale price. How do we add a column? Well, we take the name of the data frame, $sign it, and then give the new column a name, and then tell it what values are going to go into that column. And that's going to be the log base 10s of the sales prices. So we've made a column down here at the very end. We see that it's been added. If we scroll down enough, there we go. And let's get a summary of this column. So let's get a summary of the log prices and talk about it. All right, so when we do the summary, we find the third quantile, in other words, the 75th percentile. It's about 4.6. So we're not going to report this 4.6 to the boss if our boss asks for the 75th percentile. We need to unlog this value. We need to convert this back into the original scale in which the numbers were recorded. So how do we unlog something? Well, we take 10 and raise it to that power. So we'll take 10 and raise that to the 4.602 power. That corresponds to basically $40,000. So the 75th percentile is just about $40,000 after unlogging. All right, the last part of this activity wants you to look at missing values. So we've seen a lot of blanks and none are unspecifieds. And what we're going to do is hone in on 3 particular columns the columns 41 through 43. What are these? Well, let's look at the names of the dozer column in the 41st through 43rd position. We're going to look at missing value patterns in Grouser tracks, hydraulics flow, and track type. So this code is going to be provided to you as is. So we're just going to run it. We're going to replace the blanks and none unspecifies with just NAs, and we're going to run the md.pattern command from the mice package. And this lets us look for kind of how patterns appear in the missing values. What values are missing together often, which values are almost always present, etc. So here's the output in text form and then in graphical form. So let's talk about it. What do each numbers represent? Well, track type is the name of the column. A 1 represents that the value is present. A 0 means the value is missing. So this top row right here is talking about a pattern where we do have track type, but we don't have hydraulics flow, and we don't have Grouser tracks. The number to the far right says that, hey, this pattern has 2 missing values, and by the way, there's 269 rows that have this pattern. This guy down here is saying there's 602 rows that are missing all 3 of these values for a total of 3 missing values. The numbers for the column totals represent the total number of missing values for each of these 3 quantities. So 731 rows are missing track type, 991 are missing Grouser tracks, and there's a total over all 3 columns of 2,593 missing values. So how many of these 1,000 rows in the data have values for all 3 of these columns? None. Every single one of these rows is missing at least one of these 3 values. We don't see a pattern 111 here. And by the way, these are the same numbers that come out 269, 269, 9, 9. Blue means present, red means missing. Red's kind of bad, so hey, watch out. That means missing here. And this number here represents the number of missing values in that pattern. All right, so how many 1,000 rows are missing all 3 of these columns? Well, 602. And we all want to think about this. So we see a lot of the rows missing these values simultaneously. Why might this be? Turns out in this case, the questions about hydraulics flow, track type, etc. are near the end of a very long registration form. So with that in mind, you think there's a reasonable explanation for why we see these values missing quite often and together? Well, I think so. Is that, people might not have gotten around to it, answering these questions at least, especially if they were in a rush. So this just represents, hey, they didn't get to the end of this really long questionnaire, so it's no big surprise that a lot of these are just missing. These 3 are measurable quantities with each bulldozer out there. They just didn't give the responses to these. All right, so we might like to know, are any of these patterns statistically significant? If we know that, say, hydraulics flow is missing, does that give us any additional information about whether Grouser tracks is also going to be missing? Or are all these missing kind of independent of one another? So once again, we're going to run this chunk of code verbatim here and just worry about analyzing the result here. All right, so part D asks us to consider Rule 5. So what is this telling us? It has a confidence of 1, that's the value in the confidence column. It has a lift of 1.01, the value in the lift column, a support of 0.871, count of 871. So what are we going to do? We're going to talk about this stuff. All right, one thing we actually also need to know, and I didn't give this to you, I'm kind of sad about that, is we need the item frequency of our trans right here, because this tells us the fraction of values that are missing in these 1,000 rows. All right, so we want to interpret what this rule says in plain English and interpret the values of all these things here. So in English, the way that we read this pattern is basically if hydraulics flow is missing, then so is Grouser tracks. It's kind of like an if-then statement. So if we know that this is missing, then this rule is talking about the chance that this is also missing. All right, now we can do a lot more. We can do a better job at describing this story. How do we interpret this rule to its fullest? Well, all right, we want to incorporate in values of the confidence and the lift when we do that interpretation along with the item frequency of browser tracks, what's on the right-hand side of this rule. So the way that we're going to interpret this is as follows. So if we know that hydraulics flow is missing, the chance that browser tracks is also missing increases from 0.991, its item frequency. So already a big chance that this value is going to be missing. But if we know that hydraulics flow is missing in this row, the chance that browser tracks is also missing increases from 0.991 up by a factor of 1.01. That's the lift. So it's getting bigger, bumping up by a factor of 1.01 to 100%, or 1.0, the value of the confidence. So basically, this item frequency tells you just the overall probability that a row is going to be missing browser tracks. The confidence tells you the probability that that value is going to be missing after you know that the items that appear on the left-hand side of the rule are missing in that row. So once we know that the row is missing hydraulics flow, the probability that browser tracks is going to be missing goes from 0.991 to 100%. So every time hydraulics flow is missing, browser tracks is also going to be missing here. Now, that sounds pretty impressive. That's like a 100% confidence rule. Is that statistically significant? Just by random chance, it might have been the case that these missing values lined up perfectly. That's where we look at the is.significant. And since we're looking at the fifth rule here, 1, 2, 3, 4, 5, we see that yes, this rule is statistically significant. It's unlikely for chance alone to produce that alignment of missing values between these two columns, like what we saw in the data. So we would say that it does look like there's some sort of pattern going on here. So this rule is statistically significant. We see it true for the output of is.significant, indicating that the alignment of missing values in these two columns is unlikely to be due to chance alone. In other words, it's more indicative of a real pattern going on. Now, when you go and actually try to come up with smart guesses for missing values, knowing what patterns exist, what's predictive of the missingness of something else, is very useful to exploit. Now, we're not going to take it that far in BAS 474 or in our other analytics classes, but it's good to be aware of. And now we've completed Practice Set 2.